Okay, so I had actually mute myself, so that is okay. Since I forgot to unmute myself.
Okay, okay.
Yeah. So I
Good
was telling, yeah, good evening, Srihari. So I was telling about ring counter. So in ring counter, basically all the flip-flop are initially reset, and this is kind of a CISO register, serial in, serial out, shift register. So if you see at the next state equation of all the D flip-flops, so this is constructed using a D flip-flop. So you can see what Q3 plus is equal to D3. So that is the next state equation. And your D3 is actually equal to what? It is equal to Q naught. Okay. Similarly, if you see Q2 plus, so that is equal to D2. So that is Q3. Q1 plus, that is equal to D1. So that is equal to what? Q2. And Q naught plus is equal to D0. So that is equal to Q1. So initially at clock pulse 0, let us assume, okay, so initially all the flip-flop are reset. Now you can see there is a pre-bar input over here. Okay, so if I have what an active low input, what will happen? That at this particular instant, this Q3 is going to be presetted to 1. So at clock pulse 1, let this phenomena occur. So Q3 will be equal to 1, Q2 0, Q1 0, Q0 0. Now at the next clock pulse, you can see what? That Q0 means if you look at the next state equation of Q3, that will be Q0, Q2 plus will be Q3, Q1 plus will be Q2, and Q0 plus will be Q1. So this will be 0, 1, 0, 0. So these are going to shift like this. In the third clock pulse, this will become 0, 0, 1, 0. Okay. In the fourth clock pulse, this will become what? This will become 0, 0, 0, 1. Okay. And again at the fifth clock pulse, what will happen? This one, it will be feedbacked over here. So this will become 1, 0, 0, 0. Once again, the states are repeating. So you can see you started from 0, then 1, 0, 0 means what? It means you are at 8. Then 0, 1, 0, 0 means what? You are at 4. Then 2, then 1, and again you are going back to 8. Okay, again you are going back to 8. So this is what? This is your simple ring counter. So here you can see the number of U state are how many? U state are 4. There are 1, 2, 3, 4. 4 U state. Unused state, just give me a minute. So unused state are how many? Unused state, see, out of this 4-bit, means 4-bit can represent how many numbers? 16 number. So 16 minus 4. So 12 unused state. So if you want to generalize this, an n-bit ring counter will have n used state or n flip-flop, you can say. Okay. So if you construct a ring counter using n flip-flop, your U state will be how many? It will be n. And unused state will be how many? It will be 2 to the power n minus n. Okay, so unused state are all those states which we are basically not using in your ring counter. If you have any doubt, you can ask me. Any doubt? Any doubt? Okay, so the next is what? Next is your Johnson counter, or this is also known as what? Twisted ring counter. Okay, twisted ring counter. Now what is this twisted ring counter? So in your normal ring counter, you can see that your feedback is given from normal output of the last stage to your first flip flop. But over here, you are basically taking flip flop of the complement. Okay. So again, if we do the same thing, same analysis, okay. So if you do this, so over here, let us write the next state equation. So Q3 plus is equal to D3, okay, and this is equal to Q naught complement. Q2 plus is equal to what? It is equal to D2, and D2 is equal to what? It is equal to Q3. Q1 plus is equal to D1, so that is equal to what? That is equal to Q2, and Q naught plus is equal to D naught, and D naught is what? It is equal to Q1. So again, let us assume that at clock pulse 0, this is 0, 0, 0. Okay, this is 0, 0, 0. Now assume what? Okay, so sometimes they might even give you some kind of input like this. Okay, some random input means initially like 1 0 1 0. Okay, 1 0 1 0, and then they might ask you instead, by means what I am telling, that instead of starting from this preset, they will give you that this is what? This is your, means this register has this state initially. So tell us after 5 clock pulse or 6 clock pulse what will be the state. Okay, such kind of questions will be asked. So if such kind of question is asked in this particular question, so it will be what? So let me show you what happened. Q3, Q2, Q1, Q0. So such kind of input might be already there in your shift register. So at first clock pulse, this one will come over here, this 0 will come over here, and this one over here, and this 0 will be feedback. Then at second clock pulse, what will happen? This 0 will come over here. So basically, this is what is happening. Okay, let me use some different color. Okay, and this 0 will come over here. Now in the next case, this 0 will come over here, 1 will come over here, and this 0 will come over here. So 1 0, and this one will come over here. So you can see this is being repeated in just means 2 clock pulses you are getting once again. So basically this will be 1 0 1 0, and the next state will be what? This will be 0 1 0 1. Okay, and again you are back at this state. So such kind of random input might also be given to you. Okay, so don't worry. But if they have mentioned that ring counter is initialized, so you need to always consider this as a default. Okay, default case. If nothing is said, you need to consider 0 0 0 as your initial state. Okay, if there is some initial state other than 0 0 0, it will be mentioned in the question. But other than that, you always need to do what? You always need to consider 0 0 0. So now in twisted ring, you can see initially this is the case. Now what will happen? See here, even this preset is not required. Okay, this preset is not required. Why? Because automatically once you switch on the register, what will happen? You can see Q3 is actually complement of Q0. So at first clock pulse, this will be 1, remaining all 0. At the second clock pulse, this will be shifted, okay, and this 0 will come over here with complement, so that will be 1. So this will be 1 1 0 0. In third clock pulse it will be 1 1 1 0. In fourth clock pulse it will be 1 1 1 1. In fifth clock pulse this will be 0 1 1 1. In sixth clock pulse this will be 0 0 0 0 1 1. In seventh clock pulse it will be 0 0 0 1. And in eighth clock pulse this is again going to be 0 0 0 0. So you start from 0, you go to 8, then you go to 12, 14, 15, then to 7, then from 7 to 3, then from 3 to 1, and then again from 1 to 0. So how many number of U state are over here? U state. So 1, 2, 3, 4, 5, 6, 7, 8. Unused state. Unused state. So there will be total 16 combination when we have 4 bit. Out of that 8 are used. So 16 minus 8, that is 8 is unused. So if you generalize this, this will be, if you have n flip flop over here, so number of used state will be 2n, and unused state will be how many? It will be 2 to the power n minus 2n. Okay, is this clear? Tell me, is this clear? So this is what is your register, and such kind of thing might be asked in your examination. Any doubts? Any doubts, Shriyari? Anything you want to ask?
No, no, sir. Clear, clear.
Okay. So I want to ask you one thing. Just give me a second. So okay. I was discussing about this. Now let us solve few questions. So this is the first question. See if you can solve this. So all the questions I have taken, they can be solved well within like 30 seconds to 1 minute. Okay, not more than that.
Sir, I said 3 actually.
3. Okay, let us check. So this will be the level of questions that will be asked in HL. Okay. So you can see what? That initially it is given a 4-bit shift register circuit configured for right shift operation. Okay, so right shift means like this is shown below. If the present state of the shift register ABCD, that is at clock pulse 0, the state is what? It is 1 0 0 0. The number of pulses required to reach the state ABCD equal to 1 1 1 1. So I have just written the next state of this A, means A flip flop, B flip flop, C flip flop, D flip flop. Okay. So here you can see next state of A will be what? It will be A XOR with B, because this is what is happening. For B, it is what? See, why have I assumed that these are all D flip flop? Because it is given 4-bit shift register. Okay, so that is why. So in the first clock pulse, A is what? A XOR with D. So this is 1, this is 0, so this will be 1, this will be 1. Why? Because this is A only and these all are 0. In the second clock pulse, what will happen? This will be 1 still, because 1 plus means 1 XOR 0, that is 1. This one will be shifted over here, this one will be shifted over here, and this is still 0. At the third clock pulse, what will happen? Again 1 XOR with 0, so that is 1. This one is shifted over here, this one shifted over here, and this one is again shifted over here. So this is what has been asked, the number of pulses required to reach ABCD is equal to 1 1 1 1. So you can see 3 clock pulses are required. So option B is your correct answer. So this question, just a minute. So this counter is also written as ripple up. Okay, ripple up, Johnson counter or twisted ring counter. So now solve.
So, ripple up counter has nothing to do with the ripple counter?
Ripple up, ripple counter is what? Ripple counter is normal shift register, and ripple up is what? Ripple up is your twisted ring counter.
Okay, okay.
So it is said a 4-bit ripple up counter consists of flip-flops that have a propagation delay of 12 nanoseconds from clock to output. Okay, from clock to output, that means what? Means this is your clock. From clock to output, it has a 12 nanosecond delay. Okay, 12 nanosecond delay. Okay, so basically they are asking amount of time required for this counter to recycle from 1111 to 000. So at first clock pulse, so this will happen after 12 nanosecond. So this will take place, means here it will be 0 1 1 1. At second clock pulse, this will be 0 0 1 1. At third clock pulse, this will be 0 0 0 1. And at fourth clock pulse, this will be what? This will be 0 0 0 0. So this is taking what? 12 nanosecond. This will be taking 12 more, 12 and 12. So in total 48 nanosecond is required for this counter to recycle from 1111 to 0000. Is this clear?
Yes, sir, yes, sir. So, but still, I have one doubt, like,
Yes.
why it's namely ripple up counter? Actually, its sequence is going down.
Pardon?
The sequence is from 1111 to 00, so it's actually down, kind of down counting, right, sir?
See, here basically you have done what? You have started, means what was the sequence of ripple counter? Ripple up counter or Johnson counter. It was 0, then 8, then 12, then 14, then 15. Okay. Then you have 7, 3, then you have what? 1, and again you are going back to 0. So once you can see up to this point, it is increasing. Means have I skipped some step? So after 7, if 15, it will be 7, then it will be 3, then it will be 1, then it is 0. Yes. So up to this point, you can see it is increasing. Okay. But from here to here, it is decreasing. Okay. So we have taken this part. We have taken, you
Okay.
can see I have started from 15, then I went to 7, then to 3, then to 1, then again back to 0. So this much part is basically what? It is decreasing. Okay, so there is
Oh,
nothing related with frequency over here. Are you getting the point?
clear, clear, clear.
Okay, so this one, Answers? Answer? See, look over here. It is given, determine the counting sequence AB of the following counter. Okay, so you can see what this is, your synchronous counter. So in synchronous counter, for determining the count sequence, we always require what? We require your next state equation. So these are your T flip flop. So next state equations will be like this. And over here you can see TA is what? It is the input of the A flip flop, A T flip flop. So it is what? It is your B or A complement. So that is what I have written. And B plus will be what? TB XOR with B. So TB is what? A plus B. So that is what I have written. So at clock pulse 0, initially all the flip flop are reset. So 0 0. So at clock pulse 1, what will happen? So A complement plus B. So 0 complement plus B. So that is what? So you need to be quick over here. So 0 complement plus 0 XOR with 0. So directly you can write this as what? This will be 1, and over here this will be 0. Okay. So at clock pulse 0. Okay. So can you see over here? So option A has this count, option C, option D. So directly I can eliminate option B because you can see it is 0 1. So we are not getting that. So in the second case, you can see what? That this is still 0 0. So this will become 0. Okay. This will become 0. And over here it is what? A plus B. So that is 1. And B is still 0. So over here this will be 1. So out of this option, what you can see? So 0 1 here we are not getting. Here also we are not getting. Option D is correct. Now solve, if you want to solve once again. So over here you can see what? So this will be B, means directly if I write, so B is 1, A is 0, so this will be 1, and over here B is 1. Okay, so A plus B, so that is 1, and B, so this is coming out to be 0, but we are getting 1 1 over here. Why so? So this should be 1 0 we are getting. 0 0 0 1, no, 0 0 0 1 1 0, this is 0 0.
So could you explain this once more? This
Yes, I am also explaining this once again. It's okay. So let us solve this once again because I think I might have made some mistake someplace. See, these are your next state equations. Up to this point, have you understood how I am
yes,
getting all this thing?
yes, understood.
So now I am solving this. So at first clock pulse, what will happen? You can see present, these are your present state of A. So A is what? It is 0. B is what? It is also 0. XOR with A. So A is what? It is also 0. So over here, this will be 1 XOR with 0. So we will be getting 1. What about B? You can see A is 0, B is 0 in the present state. I am calculating these are my next state. So present state is 0 0 XOR with B. So over here, we will be getting 0. Tell me up to this point, is it clear? See, at the
Yes.
second clock pulse, these are your present state. This 2, A is equal to 1, B equal to 0. This is your present state. With the help of this, we are going to calculate the next state. So if these are your present state, then you can put over here A is what? 1. So 1 complement plus 0 XOR with 1. So this is 1. And over here you can see A plus B. So A is 1, B is 0, XOR with 0. So this is also 1. Okay. So you can see where is this followed. Okay. So I might have made a mistake. So option C you can see is followed. So for third clock pulse, this A equal to 1, B equal to 1 is your present state. So if you solve using this, so this will be 1 complement plus 1 XOR with 1. So this will be 0. And what about this one? So this will be 1 plus 1 XOR with 1. So this is also 0. So you are getting 0. So option C is correct. Last time I might have made a mistake somewhere. So you can see our count sequence is what? 0 0, then 1 0, then 1 1, then 0 0. So option C is correct. Is this clear, Shriyari?
Clear, sir.
Okay. This question. So what answer are we getting?
Is it 1100?
Okay, let us check. So after 6 clock pulse, okay. So at first clock pulse, you can see Q1 XOR XNOR Q0. So this two, so 1 0, this will be 0. This bit will be shifted over here, this one over here, and this over here. Next is second clock pulse. So again 0 XNOR with 1, so that is 0. This 0 will be shifted over here, this one shifted over here, and this 0 over here. At third clock pulse, again this will be 1 XNOR with 0, so that will be 0. This 0 is shifted over here, this 0 over here, and this one over here. Okay. So at fourth clock pulse, again this will be 0, and all the remaining zeros are shifted. So at fifth clock pulse, what is happening? 0 XNOR with 0, so this will be 1. Now sixth clock pulse. So after sixth clock pulse, this is only asked. So this will be 1 1 0 0. So what answer did you say, Srihari?
Same.
This 1 1 0 0.
Yes.
So this is the answer, 1 1 0 0. Okay, this one, a 4-bit Johnson counter. So this is very simple. They should have written at option D. So very simple. We know the counting sequence of a Johnson counter is from 0. So Johnson counter means what? Twisted ring counter. So then 8, then we have 12, then we have 14, then we have 15, from 15 to 7, then to 3, then to 1, again back to 0. So this is option D. Okay. So very simple question. So for this question, Pardon?
So it will be always 1, right?
Yes, very good. So this will be always 1. Why? It is given in the figure shown. The initial state of Q is 0. The output is observed after the application of each clock pulse. The output sequence at Q is. So if we write the next state equation of JK flip-flop, so you can see this will be the case. So here output is given by Y. So I have written it J is 1 and Q complement plus K complement. So K is connected to Q complement. So Q complement complement. So this will be Q dot Q. So this will be 1. So this is always 1. So option C at each clock pulse, whenever there is your positive edge, this is your positive edge triggered flip-flop. So whenever it is positive edge, what will happen? Always it will produce 1 only. So option C is your correct answer. Is this clear? Clear? Okay.
Clear.
So then let us start with ADC and DAC. Okay, what is ADC and DAC? So very briefly we are going to cover, because I don't think questions might be asked from this, because all the questions that are that come from this means ADC or DAC, they are little bit lengthy. Okay, and if you see the previous questions of HAL, means whatever is the memory based questions we have with us from different sides, so there basically theoretical questions have been asked, like what is the fastest ADC, which ADC has your maximum means error less type of solution. So all those things have been asked. So I will still try to make you understand the working of each of the circuit along with whatever is the point. Okay, along with all the points. Okay, so first is what we have is your an digital to analog converter. Okay, first what we have digital to analog converter. So what does this digital to analog converter we mean? So by
Hello, sir. Hello. Hello. It's not
I
audible.
don't know. Yes, I was muted. I don't know how. So this I am using this another device also, na. So it might have means I might have pressed it. So okay. For digital to analog converter, I was telling what at the input side we have what we have our digital bit. Corresponding to that, we get analog output voltage. So this is what this is your normal digital to analog converter. Okay, so in digital to analog converter, basically we convert a digital input to your equivalent analog output. So here there is few things that we need to know. The simplest thing is what? Resolution. So what is the resolution of DAC? It is the change in analog output corresponding to LSB bit increment. That means what? Suppose if we have a 4-bit DAC. Okay, 4-bit DAC. So 4-bit DAC means we have B, P, B2, B1, B0. So this DAC, it can take input from 0, 0, 0, like this till 1, 1, 1, 1. Okay. So the corresponding output voltage, let me assume for 0, 0, 0, it will be 0 volt. Now suppose if for 0, 0, 0, 1, so this is what? This is decimal 0, this is decimal 1, and this will be decimal 15. So for this decimal 1, if our output voltage, assume it is 0.25 volt, then you are going to say that the resolution of this DAC is what? It is your 0.25 volt. So that is what I have written over here. Okay, that is what I have written over here, that basically resolution of DAC is the change in analog voltage corresponding to the LSB bit increment. So whenever your LSB bit increment, it increments by 1, so that is the voltage, that is known as volt, means that is known as your resolution. So one more definition that we have, it is what? Voltage corresponding to logic 1, that is also known as your resolution. Okay, so voltage corresponding to logic 1, it is also known as your resolution. Now the formula for resolution is what? Sorry, VFS. So what do we mean by VFS? VFS means what? It is full scale voltage. Okay, full scale voltage. Now if assume, so here it is 20.25. Okay, assume if in our case the voltage corresponding to 0001, it was 1 volt. Okay, 1 volt. Example, another example, then your full scale voltage will be what? 15 volt. So I am telling basically this resolution is what? So whatever is the voltage of the full scale, if it is 15 volt, divided by, as we have a 4 bit DAC, so that will be 2 to the power 4 minus 1. So that is 15 divided by 15, you will be getting 1 volt. So this is what? This is the formula for resolution. Tell me if this is clear or not. Is this clear? Now the next is what? Percentage resolution. So percentage resolution, we always take it for the first bit only. So you can see over here we have 1 divided by 2 to the power n minus 1 into 100, as we want the percentage resolution. So this is the formula for percentage resolution. I am not deriving any one of the following, because direct questions will be asked based on this formula. Okay, based on the formula only it will be asked. Okay, so what I have written, okay, so this is the same thing that I have written over here, means from this formula only we can write that V full scale is what? It is equal to resolution into 2 to the power n minus 1. Now suppose in this particular case, when our resolution was 1 volt, I want to find the output for this input 1100. So what we know, output for this will be basically your resolution into what? Into your decimal equivalent of binary input. So resolution in this case is what? It is 1 volt. Decimal equivalent of 1100 is 12. So this will be 12 volt. So the output corresponding to 1100, it will be what? It will be 12 volts. So this is what I have written. Output voltage is equal to resolution into decimal equivalent of binary data. Okay. So this is what I have explained over here. Clear? Any doubt in this? So the next is what? Next is your weighted resistor DAC. So this is purely based on how good you can solve analog circuits. Okay. By looking into this circuit, okay, first let me explain you. See, basically these are your switches. Okay, these are your switches. Either it can connect in this position or it can connect in this position. So here you can see we have V reference. So this green line is V reference and this black line is grounded. So V reference, if this is 5 volt, so this will correspond to what? Logic 1, and this black color, as it is grounded, so this will connect to means this will correspond to logic 0. So each of the switches, suppose if I want to connect, like, means here you can see there are means n number of switches, so I cannot say. So suppose if we have a sequence something like this 1101, and assume this is what, this is your 4-bit DAC. So 1101 means what, this will be connected over here. Okay, so at the moment I haven't discussed which will be MSB, which will be LSB. So can you tell me, out of this B0, Bn means Bn1, which is MSB, which is LSB, which switch is MSB, which switch is LSB?
Where is actually this 1101?
Means I will be explaining at the moment. Tell me, see, these switches basically correspond to your digital inputs. Okay, digital input. So I am asking, see, this is logic 1, this green color line, and this black color line is logic 0. I am asking, if suppose this switch is connected over here, or if this switch is connected over here, so out of this n number of switches, see, our switches are from B0 to Bn minus 1. So that means there are n switches. So which switch corresponds to MSB, which switch corresponds to LSB? Can you tell me? See, your MSB has the highest contribution. Okay, like 1101. So here you can see this is LSB, this is MSB. So the contribution of LSB is what, 2 to the power 0, and that of MSB is 2 to the power 3. So it has weight of 2 to the power 3, and this has weight of 2 to the power 0. So that means what, the switch that carries the least amount of current, that will be your LSB, and the switch that carries the maximum amount of current, that will be your MSB. Now when do we have maximum current? In a branch we have maximum current when your resistance is the least. So here you can see resistance is 2 to the power n minus 1 R, and here it is 2 to the power 0 into R. So here your resistance is the least, and here your resistance is the max. So I0 will be minimum, and In minus 1 will be maximum. So this Bn minus 1 is your MSB, and this is your LSB. So did we understand this?
Clear,
Did we
clear,
understand?
clear.
Okay, so now I am telling, assume that this is your 4-bit weighted resistor DAC. So we have this 1101. So this will be connected over here 1. Even this will be connected over here corresponding to 1. This bit will be connected to 0, and this will be also connected to 1. Now corresponding to this we will have values of R. So we can calculate what will be V0. Okay, we can calculate what will be V0 with the help of normal concept of op amp. Like if we want to derive for n bit, so let me show you how to do that. See, basically at this point, if we apply node, okay, we know what, that for an ideal op amp, current going inside the op amp is what, it is 0 ampere. So if we apply nodal analysis at this node, so that will be what, minus I0 minus In, means I should have written it like this, minus In minus 1 minus In minus 2 minus In minus 3 plus If equal to 0. So this can be written as If is equal to In minus 1 plus In minus 2 plus In minus 3 till I0. Okay, now you can see what, we can apply basically your KVL in this loop starting from here to here. Why? According to virtual ground concept, this will be also 0. So V naught is equal to minus IF RFY, minus IF RFY, because we are moving from here. So if you apply KVL, this V naught I can write it like this also. So this is plus minus V naught. So minus V naught, if I start writing my KVL from here, so minus V naught, and we are moving in the opposite direction of current, so that will be minus IFRF is equal to 0. So you can see we are getting the above expression. So we already have IF is equal to what? IF is equal to IN minus 1 plus IN minus 2 plus IN minus 3 plus dot 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 till I naught. So we can also replace this by, see over here, so I can replace this IF by, so IF will be equal to what? So see over here, basically it will be equal to Bn minus 1 dot V reference divided by 2 to the power 0 r plus Bn minus 2 V reference 2 to the power 1 r plus like this B naught V ref divided by 2 to the power n minus 1 into r. Can we write it like this or not?
Clear, clear.
Okay, we can write it like this. So we can substitute what? We can substitute this IF over here to get the value of V naught. So this RF will be also given. So such kind of question will be avoided in your what HL exam, PSU exam. And if also it is given, so maximum it will be of a 3-bit question, not more than that. And all this value of RF, R, it will be given. And one more thing, they might ask you that what is the drawback in this weighted resistor DAC? Can you tell? What will be the drawback over here?
Maybe using this number of resistors, higher resolutions are actually
Yes,
a
very good.
problem.
See, we are using basically n number of resistor, n different resistors over here, starting from 2 to the power 0 r to 2 to the power n minus r, n minus 1 r. So we have in total n different number of resistor. So basically that is a very problematic circuit to create, because resistor they are bulky. So that is why weighted resistors here more number of resistance are required. So that is why this circuit is avoided. So next we have what we have is your R2R ladder DAC. R2R ladder DAC. So here also basically we have what? We have the same kind of logic, but here you can see we are using only two set of resistance. One is 2R, another is R. So this is R2R ladder DAC. So over here also you can see that this line is V reference. Now depending on your input, see, now let me ask you which is MSB over here out of this B2, B1, B0, which will be MSB, which will be LSB? Which is MSB, which is LSB? Which will be MSB, which will be LSB?
Um, I think
What do you think? Tell me. See, look over here. This B2, whatever current is flowing, it is getting the least resistance path, only a single 2R. But look over here. If this is connected over here, so it is facing many resistance path from coming from here to here. So this is your LSB and this will be your MSB. So in your R2R ladder DAC, remember the switch that is nearer to your op-amp, it will be MSB, and the switch that is farthest from the op-amp, that will be your LSB. Now this circuit, depending on the input, you can solve for your output. Okay, you can solve for output. So this will be a simple combination of analog circuit and your network theory. Okay, so you can solve it. You need to apply what? You need to apply the concept of virtual ground. And as this is what, so whatever is the input over here, you will get input over here. So if that is Vi, okay, assume if you are getting your voltage Vi over here after solving. So this is what? This is your non-inverting type of R2R ADC ladder. So V naught will be equal to Vi 1 plus Rf by R1. Okay, so Vi you need to calculate, and you can calculate it based on what is B naught, B1 and B2 and what is Vref. You will be able to calculate Vi. Okay, you will be able to calculate Vi. Just remember that current going inside ideal op amp is always 0. Okay, why? Because your ideal op amp has infinite gain, infinite open loop gain. And when it has infinite open loop gain, input impedance of the op amp is also very high. So that is why if you are able to get this Vi, you will simply get the V naught. Is this clear? So I cannot solve this over here. Okay, because if we take questions of this, it will take lot of time. So such kind of question will be asked in gate, but in PSU exams this will not be asked. So only thing they might ask you, what is the advantage of R2R ladder based on your weighted resistor DAC? So you need to say that the circuit over here, it will be not that much complex compared to weighted DAC. Why? Due to the fact that here we are only using two kind of resistance. Okay, two types of resistance we are using, and here we were using n number of resistance. Okay. Okay, next is what? Next we have is analog to digital converter. Analog to digital converter. So here basically we have one analog input.
So DAC, these two types are there earlier, right?
Yes, in our syllabus we just have DAC two types. One more type can be, see, I have constructed this R2R ladder DAC using what? Using your positive, means sorry, in your non-inverting configuration. You can see this is non-inverting configuration. One more configuration you can have is your inverting type of configuration. So that is very simple. Okay, that is very simple. Based on the circuit, you need to determine whether it is your inverting or non-inverting. So here you can see the input is applied to your non-inverting terminal. So that is why it is what? This is your non-inverting R2R ladder DAC. So have you studied analog electronics, op-amp?
I guess these kind of things, I know it.
You know.
Yes, these kind of things. Yes.
So that is okay then. Then it's fine. So you don't require then any more concept regarding this. Okay. So here what we have? We have a analog input. Corresponding to this, we get what? We get your digital output. Okay, so this is what? This is your analog to digital converter. Now in this, we have four kind of analog ADC: counter type, successive approximation type, flash type, dual slope type. Out of this, the most important are these two. Okay, so this type HL questions might be asked from this. I will tell you why. See, this is your flash type DAC. Okay, flash type DAC. So sometimes you might also see, so this is the circuit for Means I should have drawn it before only. So this is basically a D flip flop. Okay, D flip flop we have over here. So clock. See, flash type DAC, basically it takes help of comparator and resistors. Okay, comparators and resistors. This is basically a 2-bit analog to digital converter. So here we have combination of resistance that are connected like this. So the corresponding voltage at this point, it will be what? As you know that current going inside op amp, it is 0. So all this four resistance, they are connected in series because no current is flowing from here. So R and R, they are all in your series. So we can apply what? Voltage divider theorem. So over here, voltage will be, if this voltage is V reference, so this will be V ref by 3 by 4 V ref. Over here, this will be what? V ref by 2, because R and R are below and we have in total 4R. And over here means, so V1 will be equal to what? According to voltage divider theorem, it will be V into R1 divided by R1 plus R2, and V2 will be equal to what? It will be equal to V into R2 divided by R1 plus R2. Okay, so these are what? These are your, this is your voltage divider theorem. Same thing I have applied over here. Okay, so now you can see what? I have divided the voltages, and this VA is basically your input analog voltage. Input analog voltage. Now why this D flip flop? See, when we have, suppose, so I will tell why. Suppose if this VA is less than Vref by 4. So these are your comparator. Okay, in a comparator, this is your non-inverting terminal, this is your inverting terminal, this is your output. So whenever non-inverting terminal has a greater voltage than inverting, V naught will be equal to plus Vsat, and here plus Vsat corresponds to logic 1. And whenever V non-inverting is less than V inverting, V naught will be equal to minus Vsat, and here minus Vsat corresponds to 0. So I am telling what? VA is less than Vref by 4. So that means what? If this is V less than even Vref by 4, you can see all the non-inverting terminals are what? It is less than your inverting terminal. So everything will be 0, 0, 0 over here. So for this, basically B1, B0 will correspond to 0, 0. Now why this D flip flop? See, there might be some finite amount of propagation delay in this comparators. Okay, comparator. So I should have written it as C3, C2, C1. Okay, so there might be some propagation delay in this C3, C2, C1. So what happens to synchronize the output of this? We are supplying what? We are giving one D flip flop in between this comparators and encoder. Okay, encoder. Now assume if VA is greater than Vref by 4 but is less than Vref by 2. So what will happen? This flip flop, its non-inverting terminal has a higher voltage because VA is greater than Vref by 4. So this over here has a higher voltage than the non-inverting, but here it is less. So this will correspond to 0, 0, 1. So this will correspond to 0, 1. Next will be what? If VA is greater than Vref by 2 but is less than 3 by 4 Vref. So this will correspond to 0, 1, 1, and this will be 1, 0. Last is when Va is greater than 3 by 4 Vref. So this will be 1, 1, 1, and the corresponding output will be 1, 1. Okay. Tell me if this is clear or not. Is this clear? How basically we are converting? So this operation might not be asked. Okay. Operation might not be asked, but few things that might be asked are, for n-bit comparison conversion, the number of comparators. So over here you can see for a 2-bit binary output, we required 3 comparators. Similarly, if you had 3-bit, for 3-bit you will be required 2 to the power 3 minus 1, that is 7. For 4 bits, you will be requiring 2 to the power 4 minus 1, that is 15 comparators. Similarly, the number of resistors for 3-bit, it will be what? It will be 8. For 4-bit, it will be 16. So these all questions might be asked, that for a flash type resistor, okay, so what are the number of comparators that we use, or what is your basically the number of resistors that we use. Okay, and this is also known as parallel comparator. Another name for flash type is what? It is also known as parallel comparator type ADC. Okay, so this is very important. This too, in all the objective kind of exam, you will find one or the other question from this two concept. And this flash type ADC, okay, flash type ADC, it is the fastest ADC. Okay, and conversion time required over here is just one clock. If one of the clock has time period TC, so you will get the output within 1 CLK, 1 clock time. So conversion time is what? TC. That is 1 clock time. Is this clear?
Clear.
Okay, so this is the fastest, but we usually don't use this for higher number of bits due to the fact that basically the circuit will become very cumbersome. You can see over here that we require 2 to the power n minus 1 what? Comparators. Along with that, we require a series of resistors, something like this, and I have already told you that resistor circuit are bulky. Okay, so we usually don't use this. So the next is important thing is what? Dual slope integrating type ADC. Okay, dual slope integrating type ADC. So let us assume over here that we have a 3-bit ADC, 3-bit, or you can even assume 4-bit, it's okay. So let me first tell you how this circuit works. Okay, how this circuit works. See, very carefully see. Suppose we apply VA. Okay, so over here let us assume 0 0 0 corresponds to 0 volt, 1 1 1 1 corresponds to 15 volt. I am just telling that we know this. Okay, we know this. Now look very carefully. Suppose if I give this VA as 9 volt. Okay, 9 volt I give in the first case. So what will happen? So see very carefully the working of this circuit. So this circuit, initially when we have to measure, we connect this VA from, means this integrator, this is connected to your VA. Okay, and we have a switch over here. This switch basically what it does, it transmits it from VA to minus VR, but we will see when that transition happens. At the moment, initially you consider that this is connected to this integrator circuit. So this is basically what? This circuit is your integrator. So when we apply VA is equal to 9 volt, what will happen? So this capacitor will start charging. Okay, this capacitor will start charging, and you can see we have a comparator over here where the non-inverting terminal is what? Non-inverting terminal is grounded, and as this capacitor is charging, So inverting terminal, it will have what? It will have a higher voltage compared to your non-inverting. So over here we will have one positive signal, and from here we have clock. So see very carefully. Basically what is happening? We have a negative signal from here, because this is what? This is your integrator circuit, and we know what? This is your non-inverting integrator. Means integrator is usually non-inverting. Sorry, I am what I am telling. So this is your inverting circuit. Why? Because you can see input is being applied to your negative terminal, and this is fed to your this comparator. So this is negative always during this charging time, because capacitor is charging. This is negative, this is 0. So V non-inverting is always greater than V inverting during this charging phase. Tell me up to this point, is it clear?
Okay.
Is this clear? So V naught will be what? V naught will be equal to minus 1 by RC integration of this whatever is VA dt. Okay, so this will be the case. So you can see this is always negative and this is 0. So over here your output will be always 1. Okay, so along with that we have clock pulse. So what will happen? This V naught, it will charge up to what time? It will charge up to, you can see this is 1, and this clock, it is what? It is constantly supplied, and this is your normal up counter. So I have said what? That this is your 4-bit up counter. So it will keep on counting, and you can see the MSB of this counter is connected to a T flip flop that is your negative edge triggered. And you can see this is basically getting its negative edge from the MSB of this up counter. Okay, so if you have one up counter, so see very carefully, how will it look? Means when will you get, at what condition will you get the negative edge of this MSB? See, basically you are counting from 000, then 0001. So let me write it very quickly. 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8. So understanding the circuit is very important, even if it is not going to be asked in your exam still. Okay, so look, this MSB, the negative edge of this MSB will serve as your trigger for the T flip flop. So you can see that negative edge we will get after this one. After this one, why? Because after 1111, see, if this is your LSB and this is your MSB, if all of them are 1 1, so MSB you will go to, after 1111 you will go to 000, and when you go to 000 you can see that this is your negative edge, because you are going from 1 to 0. See, this is not negative edge when you go from 0 to 1. If you see, if this is the MSB, if you go from 0 to 1, this is your positive edge. But when you go from 1 to 0, you are going from where? You are going from your positive, means from a higher state to a lower state, so you will be getting negative edge. So after 2 to the power 4 clock, after 2 to the power 4 clock pulse, what will happen? This flip flop will get the negative edge for the first time, and when you get the negative edge, here you can see initially this was 0. When this is 0, VA means VA is connected to this ideal integrator. The moment you get this negative edge, this output will become 1, and at that very instant this switch it will be connected to your minus Vr. And the moment this gets connected to minus Vr, you can see this capacitor, it will start to discharge from this path. Okay, it will start to discharge in this path. Is this clear? Tell me. Is this clear, Srihari? The working of this circuit?
One more time in the before the toggle flip flop, that up
See,
counter section.
I am telling what this up counter will keep on continuously counting. It will count from 000 to 111. The moment, once again, you know what a normal up counting sequence, a 4-bit up counting sequence, it will go from 0 to 1111, then again from 1111 to 0000. So over here you will get one negative edge, and this negative edge, as you can see, this is one toggle flip flop. Initial state of the toggle flip flop was 0. When the initial state is 0, this switch will be connected to VA. The moment it gets the negative edge, this toggle flip flop will toggle from 0 to 1. When this is 1, this switch will be getting connected to your minus VR, and when this is connected to minus VR, basically your capacitor will get one discharging path from because here you can see it is 0. Here you can see due to virtual ground, means this point is 0, and over here you can see as this is 0. So what will happen, this capacitor will get one path of discharging in this way. Are you getting my point? So this capacitor will start to discharge. Tell me if this is clear or not.
Yes, the current will flow in the backward direction, right?
Yes, backward direction.
Okay.
Okay, so it will again do what? It will again discharge to minus VR. Okay, it will discharge to minus VR. But look what happens. See, here I have taken 9 volt. Even if I had taken 10 volt, so this capacitor, it would have charged till your what? 2 to the power 4 clock cycle. So your charging time of this capacitor is fixed. It is fixed. So here, as we have 4 bit, so it is 2 to the power 4 clock pulse. Now if this was n bit, so your charging time is fixed. So for 9 volt, assume if VA is 9, so let us assume that it is charging up to this point. So this is 9 volt. Even if this was 10 volt, this capacitor would have charged more. Okay, so this would have been 10 volt. Why? Because the charging time is fixed. You can see charging time is what? It is 2 to the power n clock cycle. So for more value of VA or less value of VA, suppose if 8 volt was applied, so 8 volt will come over here. As charging time is fixed, but the amount of charge the capacitor is getting, it will be less when it is 8 volt. When it is 9 volt, it will be little bit more. When it is 10 volt, it will be a little bit more compared to that. Tell me if it is clear or not. Is this clear? Are you understanding? But
Yes,
look, when we are discharging, the capacitor, means the value capacitor, when it has minus 8 volt, it will take less time to discharge. Compared to minus 9 volt, it will discharge taking a little longer time, and this will take a far more time compared to this. So this time are basically compared to give us what? To give us the corresponding what? To give us the corresponding output. So how do we get this output? So look over here. What happens when this is discharging? Okay, after this point, when this is discharging, what is happening? You can see this is 0. Okay, this will be 0 because this is sorry, very sorry. See, this is still 0. This is still 0, and my capacitor is discharging. Suppose if it is 9 volt, minus 9 volt, so it will discharge again to minus 8, minus 7, minus 6, like this to 0. So this terminal is still negative. So clock is 1, means this clock I am telling, this output is 1, clock is 1, so this counter is still counting. Suppose for 9 volt, this will count from, means minus 9 volt will correspond to what? It will correspond to, means what I should be explaining it like, see, once it has started discharging, so minus 9 will be corresponding to 0 0 0, because my counter, it has reset it to this point. So over here at this point, counter was what? It was 1 1 1 1. Now minus 9 volt corresponds to 0, minus 8 volt will correspond to 0 0 1. Like this, minus 7 will correspond to 0 0 1 0. Like this, the moment this V naught goes to 0, this V naught goes to 0, at that precise moment, what will happen? This terminal is also 0, non-inverting, and this is also 0. So the moment these two are 0, over here we will get 0, and this will become 0, because one of the input of AND gate is 0. So our count will stop, and this count, whatever we get, minus 1 0 0 1 or 0 0 1 1, whatever is the count we are getting, we will say that for the corresponding voltage we are getting this count. Tell me if this is clear or not. Is this clear what I tried to explain? Shriyari?
I think for the last,
See, I will explain once again. I will explain once again. See, at this point, what happens? I told you the next state will be 0 0 0 0. The moment this is 0 0 0 0, what will happen? This toggle flip flop will get a negative edge. Due to this negative edge, this switch will be connected to minus VR, and the moment this is minus VR, this capacitor, it will start to discharge. Capacitor have some initial value. Okay, it has some initial value. It is some negative value that we have. Okay, it is some negative value that we have. So that is what, let us assume that it is minus 10 volt that has been stored. So this particular case I am taking. Okay, this particular case I am taking minus 10. So over here you can see this is minus 10 volt, this is 0. So now your capacitor will discharge, but you can still see your non-inverting terminal has a lower voltage compared to inverting. So output of this comparator is still 1. Now this will be doing what? This is discharging from minus 10 to minus 9.9, minus 9.8, like this till 0 it will go, because less than 0 it cannot go. I will even tell you that why. It can go up to 0. Now the means while it is discharging, you can see this is at a lower potential than this one. So output of this comparator is still 1. So when this is 1, if clock is supplied, so output will be 1. So at each clock instant, this counter will be up counting from 0 0 till the point this voltage reaches 0. Okay, so let us assume that this point, at this 0th point, my counter has counted to 1010. So this is now telling us that minus 10 means this 10 volt has corresponded to 10 volt. Why? Because this discharging, during discharging, this counter was also counting that at what time basically this capacitor is completely discharging. Now tell me, is this clear? Is this clear?
Yes,
Now
sir.
is this clear? So while this capacitor was discharging, this counter was still on. Why? Because it was getting a positive edge over here due to this clock pulse being 1 over here. So whenever we get 1, so that means what? This up counter is still counting. The moment it will get 0, your counter will stop counting. So when will we get 0? When this capacitor has completely discharged and when we get 0. So the moment we get 0, inverting terminal, non-inverting terminal, it is at same voltage. So output of this comparator will be minus Vsat. Minus Vsat means minus V set corresponds to 0, and if one of the input of AND gate is 0, output will be 0, and if this is 0, your up counter will immediately stop counting because it is not getting any clock pulse now. So that is why it will hold the state, and whatever is the holded state, that state will correspond to this voltage. Tell me now if this is clear to you or not, whatever I have discussed here. Did you
Clear.
understand?
Clear.
Clear?
Yes.
So now listen very carefully that this is known as your charging time. Okay, charging time. Okay, this is known as your charging time, and this is known as your, for the corresponding 10 volt, this is your discharging time. Okay, discharging time. Okay, fine. So now this capacitor, how much will it charge? How much will it charge? So you can write it like this. If this current is I, okay, so I is equal to what? I is equal to VA by R, and we know what? Capacitor current is equal to what? C del V by del T. Okay, so this current I is your capacitor current. This current I is your capacitor current. Why? Because 0 ampere is flowing in this. So we can write what? We can write basically IC is equal to I, and that is equal to C del V. So del V means this is your positive side. So 0 minus this is what? V naught by del T. So 0 is what? When 0, when we have 0, we have at the starting point, V naught we have at this time. So let me assume that it is T1. So you can write basically this will be what? So your charging means, sorry, this I will be equal to what? It will be equal to VA by R is equal to minus CV naught by T1. So this V naught is this value. Okay, corresponding to 10 volt, whatever is this value, we are calculating this one. So generalized way I am calculating. So that will be equal to what? V naught is equal to minus 1 by T1, and this will be equal to what? Sorry. So this will be 1 by RC T1. Okay, 1 by RC T1. Tell me if this is clear or not. Is this clear, Shriyari? No.
VA,
I cannot hear you clearly.
the VA is not there in the expression.
What VA? Okay, VA is not. So VA, it will be over here. VA by RC. Okay, sorry, I forgot to write. So this C will come over here and this T will go over here. So this is what? This is your charging time, means the voltage at this point. Okay, voltage at this point. Now next is what? Discharging. Okay, discharging. So discharging, if you want to write, how are you going to write it? See, this V naught, now it will be basically equal to what? It will be equal to V naught. See, even this RC, I could have written it like the time constant. So I can even replace this V naught is equal to minus VA by tau T1, where tau is what? It is the time constant of this integrator. So now next what I can write, while discharging, if you want to write this, so V naught, so use this equation. If you tend it backward, so this will be what? It will be equal to minus VA by tau T1 plus, okay, plus VR. Why VR? Because this capacitor, it can discharge till VR. Okay, it can discharge till VR. VR by tau, and over here this is T minus T1. So T1 is what? T1 is this time 2 to the power n. This is your T1. So I have just written the equation for this line. If it is corresponding to your 10 volt, I have written this. Okay, tell me if this is clear or not. I have just written the simple equation, that's it. Is this clear?
For the case 10 volt, it's written.
Yes, not for the 10 volt. I am saying that this is some generalized case. Assume this is any volt V naught. V naught. Assume it is V naught. For this line, I have written the equation. See, initially you are at this point. See very carefully what I am telling. Initially you are at this point. Okay, so I have written the initial value. And this slope is what? This is your increasing slope. Increasing slope. Okay, increasing slope. So how much are you, means how much value can you go? You can go up till minus Vr. So Vr by tau. Now why this tau? Because this is the time constant of this RC circuit. So Vr by tau, t minus t1. Why? Because after t1 you have taken, and I am assuming that this is going up to t, so that is why I have taken t minus t1. In this duration, this much voltage is decaying, so that is why I have taken t minus t1. Now is this clear?
Yes, sir.
Okay, is this clear? So now let me assume this is t2 at this point when it is again going back to 0. So look at this equation. At this equation, if I put t equal to t2, so what will happen if I put t equal to t2? V0 will become equal to 0 minus Va by tau t1 plus Vr by tau t2 minus t1. So tau tau will be cancelled. You can remove it. So what you get? Vr t2 minus t1 is equal to what? Va into t1. Now this is the most important result that we have. So Vr is what? Reference voltage. So this will be given in the question, into t2 minus t1. See, this whole time is t2. This whole time is t2. So let me draw it over here. This whole time is t2 and this is t1. So t2 minus t1, look what I have written. This is your discharging time. So this will be reference voltage into discharging time is equal to what? Va is what? Va is your input voltage. Input voltage into T1 is what? Charging time. So you already know your reference voltage, you know input voltage, you know charging time, because if it is a 4-bit, charging time will be 2 to the power n TCLK. Okay, so you know everything. You just need to get the discharging time, and discharging time corresponds to what? Corresponds to the counter of this bit. So they will tell you basically that if this up counter is counting from 0000 to 0001 in like 10 microsecond, and if you, after from this calculation, if you get discharging time as 100 microsecond, so this corresponds to basically what? There are 10 state change. So 10 state change. So 10 state change in up counter means what? 1010. So from this discharging time, you can basically calculate what will be the output of your up counter, or what will be the corresponding bit change for your VA. Is this clear operation? How it is working?
Clear, clear.
Are you sure? Is this working clear?
Yes.
Okay. So this is, this basically this integrator or dual slope type. Okay, dual slope type where I have written. Okay. So dual slope type ADC, sorry, it is what? It is your slowest. Why slowest?
Because of the capacitor and all those things.
No, it
Yeah.
is slowest because if you calculate the maximum converting time, so that will be what? That will be equal to charging time plus discharging time. So charging time is fixed 2 to the power n TCLK. Now what about discharging time? So discharging time, you look that the moment you switch from 111 to 000, this state is not actually calculated, because at this precise moment what happens, this is going to 000 for the first time and you get the negative edge, so you get this signal that you need to connect the switch to minus Vr. So only this state is not counted in your up counter. Other than this, all the other states will be counted. So this will be 2 to the power n minus 1. Why minus 1? Because when you go from 1111 to 000, you are not counting that. Okay, you are not counting that state. So that will be 2 to the power n minus 1 TCLK. So if you solve this, this will be what? 2 to the power n plus 2 to the power n minus 1 TCLK. So this will be equal to 2 to the power n minus 1 TCLK, or approximately in examination you can even write 2 to the power n TCLK. So this much time is the maximum conversion time of this DAC. Okay, of this, and sorry, DAC I am telling, of this ADC. Okay, did you understand?
Yes, sir.
Okay, so this is the maximum, but this kind of dual slope ADC, basically it has your highest error free result you will get from here. Okay, so the very precise results you are going to get from dual slope integrating type ADC. All the multimeters, they have dual slope integrating type ADC, where your precise answer is required, precise voltage measure means precise output is required compared to the time. Okay, okay, fine. So next is what we have, a counter type ADC. So this is the simplest kind of means ADC. So what happens, look very carefully. Suppose if we have a counter that has resolution of 1 volt. Okay, now assume in this counter type ADC, what I am telling, that I want to convert this 6.5 volt, okay, 6.5 volt to corresponding binary bit. So how are we going to do? Look very carefully. If this is 6.5 volt, so look over here, this 4-bit counter, this is also 4-bit up counter. Okay, 4-bit up counter, it is counting. So here I have taken 4-bit, I should have taken 3 bits only. So let me erase one of the bit, because in our example we have taken 3 bits. So let me erase this. So look what happens. Initially all the counter are resetted to 0. Okay, all the counters, everything is resetted to 0. So if this is 000, what will happen, this is your digital to analog converter. Okay, digital to analog converter. I'm very sorry what I am doing. Okay, so this is digital to analog converter. So for this DAC, what will happen? As you are getting 000 as input, your output voltage V naught, it will be what? It will be 0 volt. So over here you have 0 volt, you have 6.5. So output will be 1, and this is clock. So this counter, why have I taken a NAND gate? So this is one AND gate. So this is high clock pulse. So whenever this will get one clock, it will count up. So in the next state, it will be what? It will be counting 001. So when it is 001, I have given the resolution of DAC as 1 volt. So this will be 1. This one will come over here. Still you can see this is 6.5. This is 1. So again this will be 1. And here it will be 1. In the next clock pulse, this 4-bit counter will count once again. One more state. Okay. So 010. For this it will be 2. So 2 will come over here. Like this it will go till 110. So at 110, what will happen? This is 6 over here, 6 volt. Still you can see what? That output of this comparator, it will be 1. Why? Because here we have 6 volt and this is your input voltage 6.5. So one more count sequence will take place, that is 111. But for 111, this ADC will produce 7 volt, and when this 7 volt come over here, so 7 in the non-inverting terminal and your 6.5 in non-inverting, so this will generate 0, and the moment this is 0, output of this gate will be 0, and this counter will stop counting, and basically we have a latch over here. So this latch basically stores the present state. So the present state was 1100. 111 would have been the next state if here we would have got 1. But this is what? This is your present state. So your latch has stored this present state. So for the 6.5 corresponding to 6.5 volt, our output of this latch will be 110, and this will be the corresponding output of this 6.5. Tell me if this operation is clear or not. Working operation, counter type ADC. Is this clear, Srihari? Any doubt? Okay. So the next what we have? Next is your successive approximation type. So here also, okay. So maximum conversion time will be what? Maximum conversion time, if this is your 3-bit, so that will be 2 to the power 3 TCLK. Okay. If it is n-bit, maximum conversion time will be 2 to the power n TCLK. So note this, over here maximum conversion time is what? For a counter type ADC, it will be 2 to the power n TCLK. Now the next is what? We have successive approximation type resistor. So this is also like counter type ADC only. Only thing is that instead of this 4-bit counter, we have over here is what? We have over here is SAR unit, successive approximation registers we have. So basically what it does, suppose if I want to calculate 6.5 volt. So here also I am telling that this DAC has a resolution of 1 volt. So look, initially what will happen, that this SAR, it has all the bits what? Resetted. Now the moment first clock pulse is applied, what will happen? The first MSB bit will be changed to 1 and remaining will be 0. Now for this 100, the corresponding output of this DAC will be what? It will be 4 volt. Sorry. So this will be 4 volt. You can see 6.5 is greater than 4. So this will be 1. So this SAR, what it will do, in the next clock cycle, it will increment the next bit position to MSB. So this has been incremented. So for this bit position, this DAC will produce what? It will produce 6. So again this 6 volt will be feedbacked over here. You can see what? That this 6.5 is greater than 6. So output of this comparator is going to be 1. And if this is 1, so the next clock cycle will again be supplied to SAR. So what will happen? So the next bit position will be changed to 1. So when this is 1, this will become 7. So here this is 7 volt. Here it is 6.5. So this will be 0. So if this is 0, the SAR, it will not do anything. Basically, whatever is the value that has been latched, that is your this state, it will be given as your output. So simple. Here basically what we have, here we have basically, you can see that this is counting one by one, but here we are not counting one by one, we are just incrementing one of the bit position. Suppose if here it was 3, if it was 3 volt, if it was 3 volt for this particular case. Okay, so how will this counter, means how will we get the output? So look over here. Okay, how will we get? Basically, if it is 3 volt, so initially all the value of SAR is 0, 0, 0. Corresponding to this will be 0. So 0 is over here. You can see output of this comparator will be 1. So clock will be supplied to this SAR, and whenever this SAR gets clocked, so the first MSB bit will be incremented to 1. So this corresponds to 4. So when this is 4, this 4 will come over here, and you can see this is 3 volt, this is 4. So immediately what will happen? This is going to be 0. And if this is going to be 0, your SAR immediately knows that what we have chosen is wrong. So what it will do, it will, in the next clock cycle, it will reset this to 0, and this next bit will be set to 1 in the very next clock pulse. So when this is happening, this corresponds to 2. So this 2 will come over here. Okay, this 2 will come over here. So you can see again 3 volt is greater than 2. So this again it will go to 1. So if this is 1, what will this SAR do? It will basically increment the next bit. So that will be 0, 1, 1. And this is what? This is 3 volt. So the moment this DAC produces 3 volt, you can see what? This will again become 0. But this time your SAR, it will not make this 0. Why? Because it already knows that we have reached the LSB position. So this is our final case. So this output has been latched previously. So this latch will give output corresponding to 3 volt as 0, 1, 1. So the maximum conversion time over here, it will be NTC. Okay, it will be NTC. Tell me if this concept is clear or not. Is this concept clear? Okay, so we have here is few questions. Okay, few questions we have. So one by one, let us solve them. So already it is 8. So what I will do, so I will post this question in our group. You can try this question one by one, or else I will be solving this question and sending you the solution in our group. Okay, so it's already 8. You guys have your next class from 8:30. So I will leave you. These are very simple questions. Okay, very simple question. Like integrated output waveform of the dual slope ADC is shown in the figure. The time t for an 8-bit counter with 4 megahertz clock will be. So here the time t they are asking for what? For a 8-bit counter. So for 8-bit counter, your they are basically asking you the charging time. So charging time is what? It is equal to 2 to the power n Tc. So 2 to the power 8 into Tc. Tc is given, means frequency of the clock is given. So that will be, time period of the clock will be 4 into 10 to the power 6. So this will be 2 to the power 6 into 10 to the power 6. Sorry. Yeah. So this is going to be what? 64 microsecond, or over here it is given in milliseconds. So this will be 0.064 millisecond. So option B will be your correct answer for this question. So the next question is also very simple. Here it is given a 4-bit successive approximation ADC has an input voltage range of 0 to 15 volts. Okay. The sequence of state, the successive approximation ADC will transfers for analog input of 13.26 volts. So here a 4-bit ADC is given. So 4-bit means what? From 000 to 111 it will count, and here voltage range is from 0 to 15. So this will be 0, this will be 15 volt. That means resolution is what? Resolution is 1 volt. So if resolution is 1 volt, initially the bit count of SAR will be 0. So this is for clock pulse, 0th clock pulse. At first clock pulse, the MSB bit will be 1, 1, means 1, 0, 0. So for this, the voltage will be what? It will correspond to 8. So it is still less than the desired voltage. So in the second clock pulse, your SAR will do what? It will increment the next bit. So for this, you get 12. Okay. Still, this is less than the desired voltage. So in the third clock pulse, what will happen? We will increment the next bit. So you can see we are getting 14, but this is wrong. We require 13.26. So what will happen in the fourth clock pulse? This will basically do what? SAR will keep this two intact, because up till this point it was less than the desired voltage, but at this point we increase the voltage than the desired voltage. So this will again go to 0, and the next bit will be incremented to 1. So you can see corresponding to this we get 13 volt. Okay, so this is the desired result which we get. So here basically they have asked what will be the sequence. So first will be 1000, next will be 1100, next will be 1110, and after that 1101. So where we see over here we get triple, no, this is wrong, 111. Yeah, this is correct. See, after this point we are getting this. So this is the correct answer. Similarly, over here it is asked the number of comparator in a 4-bit flash type ADC. So that will be what? 2 to the power 4 minus 1.
So one more time it is written.
It is written one more time because you know what? Here they have asked what? The successive approximation. Basically, this time your latch has been activated. Okay, this latch has been activated over here. So one more count will be required. Actually, one more count of this clock is required to generate this output. Okay, so that is why this is written one more time. So here you have what? Your answer is 15. Next is what? The advantage of using a dual slope ADC in a digital voltmeter is that conversion time is maximum for dual slope. Accuracy is high. So accuracy is very, very high, and it does not require a comparator. This is very wrong. We require one comparator in your dual slope type ADC. So this is wrong. It gives output in BCD format. This is also wrong. We get output in your binary. Okay, normal binary, not binary coded decimal. So option B is your correct. It gives the highest accuracy. So next question is what? In a 3-bit counter type A to D converter, resolution is 0.025. The digital output for 1.13 volts. So this is very simple. This is a counter type A to D converter. So 3-bit means what? From 000, it will count till 111. For 000, your count will be what? So resolution is 0.025. So this will be 0 volt. For 0.001, it will be 0.25. Okay, so for 0101 it will be 0.5. So they are basically asking for 1.13 what will be the count. So for option A, as it is 3, so it will be 0.75 volt. This is what? This is your 6. So if you do that, that will be 1.5 volt. 0.25 into 6 is 1.25. Sorry, 1.5. This is what? This corresponds to 4. So this will be 1 volt. This is 5. So 5 will correspond to 1.25 volt. So the nearest you can see is 1.13. So you will mark option D as your answer. Okay, option D as your answer you will mark. Is this clear?
Clear,
Is
sir.
this clear?
But 2 questions before I have missed, I think, the question.
Which one? This one?
No, right.
This one?
Next one.
This one?
Yes.
So here the number of comparators in a 4-bit type flash ADC is asked.
Okay.
So that will be 2 to the power n minus 1. If resistance is asked, so that will be 2 to the power n. So that will be 16 number of resistors will be asked. Okay. So such kind of questions will be asked in your HAL type of exam. Is this clear?
Clear.
So with this, we end our digital. So from Friday's session, we are going to have control. Okay. So digital, this much is only required.